Good morning. We continue with single leg graph freedom systems, and I think we should continue with Rayleigh's method with one example. Okay, here we have a system. We want to obtain the natural frequency for this system by using the Rayleigh's method. There is a cylinder of mass m and mass moment of inertia j, which is connected to a spring of stiffness k and rolls on a rough surface as shown. Use Rayleigh's method to find the natural frequency of the system for small displacements. Using the Rayleigh's method, we need to obtain the energy terms for this system, the kinetic energy and potential energy. Here we have a cylinder, as you know from the dynamics from MM366, we know that the kinetic energy for a rigid body is equal to the half times by the mass of the rigid body times by the velocity of the mass center squared plus half times by the mass moments of inertia about the mass center times by theta dot squared, which theta dot is the angular velocity of the rigid body. So anytime when the rigid body does not have any rotational motion or does not have any rotational uh, um, velocity or angular velocity, the kinetic energy includes only the translational part, which is half times by the mass times by the velocity of the mass center squared. But here we have a cylinder which at the same time when it's rotating about its center, it has a translational motion by x. Here, because the motion of the cylinder is without slipping and the surface is a rough surface, so we can assume that the velocity of the center here at this point is equal, or the displacement of course, it's equal to r times by x, and consequently the velocity of this point is equal to r times by theta dot. So we can write for this system, we can write that x is equal to r, which is the radius of the cylinder, multiplied by theta, r theta, and we can conclude that x dot, or the velocity, is equal to r theta dot. So the first point is that this system is a single degree of freedom system because x is not a independent parameter. In fact, x is a function of theta. So we can define the displacement or the position of each point of this system using one parameter, which here we use theta. So we can use theta to define all of the displacement and velocities. And also by using the theta, we can write the kinetic energy and potential energy for this system. As I told you, the translational displacement is equal to the radius times by theta because there is no slipping during the motion. So the potential energy here, we only have one spring with the stiffness K. And if we assume that this is the datum level for the gravitational potential energy, and at this level, if we assume that the gravitational potential energy, which we call it, for example, UG, is 0 at this level, during the motion, you can see that the mass center of the cylinder will be remain on this datum level. So during the motion, UG, or the gravitational potential energy, is equal to 0, and only we will have the potential energy is stored in the spring, and it's equal to half times by k times by x squared, which x is equal to r theta. So this is the potential energy during our vibrating motion, half k r squared theta squared. For the kinetic energy, as I told you, we will have half times by mass times by the velocity of the mass center squared, which the velocity of the mass center squared is x dot here, and x dot is equal to r theta dot. So T is equal to half m r squared theta dot squared plus half times by the mass moment of inertia about the mass center times by the angular velocity squared, which angular velocity is theta dot. Here we have the angular displacement, which is theta, so angular velocity is theta dot. And finally, the kinetic energy is this term, half m r squared theta dot squared plus half j theta dot squared, which j is the mass moment of inertia for this cylinder about its mass center. And we can simplify the kinetic energy as this equation, half times by m r squared plus j times by theta dot squared. Now we can assume that theta, or the response for this system, is a harmonic function. For example, theta, uppercase theta, times by cosine omega nt, which omega n is the natural frequency of the system. And if we substitute this theta for u and t, or for potential energy and kinetic energy, the potential energy is equal to half k r squared times by theta squared, which theta will be substituted from here, and it will be uppercase theta times by cosine omega nt. And we can conclude that the maximum value for the potential energy is equal to half k r squared uppercase theta squared, because cosine omega nt is between -1 and +1. So the maximum value for cosine omega nt squared is equal to 1. And we can substitute here, instead of cosine omega nt, we can substitute 1 to achieve the maximum value for the potential energy. For kinetic energy, we will have the same scenario. This time, instead of theta dot, you should substitute from this theta. The theta dot is equal to uppercase theta, which is a constant value, times by cosine omega nt. The derivative of this term with respect to time is equal to minus uppercase theta times by omega n times by sine omega nt. This term, this is theta dot. Similar to the potential energy, to achieve the maximum value of the kinetic energy, this sine omega nt squared must be maximum, and the maximum value for a sine function, as you know, is equal to 1. So we substitute 1 for sine omega nt squared, and we will have half times by m r squared plus j times by omega n squared times by uppercase theta squared. Now, to obtain the omega n, these two values for the maximum potential energy, this term, and the maximum kinetic energy must be equal. When these two equations are equal, you can conclude that omega n is equal to a square root of this term, which is the natural frequency of this system. So you can see, in a single degree of freedom system, you can easily find the natural frequency using the potential energy and kinetic energy directly, without solving the equation, without extracting the equation. I mean, here we did not extract the equation of motion. We did not solve any differential equations, and directly from the energy terms, potential and kinetic energy, we extract the natural frequency of the system. Okay, any question? Is it clear so far? Okay. The next example, here again we have a system with one mass m, two springs K1 and K2. We want to find the natural frequency of variation of a spring mass system arranged on an inclined plane as shown. Here we want to obtain the natural frequency for this system. Of course, this time we don't want to use the Rayleigh's method. So we can extract the governing equation, the equation of motion. Then we can solve it, find the natural frequency or the eigenvalue for the equation. For this system, here you can see we have a system with some initial deflection. I mean, because it's not a horizontal system and we have an angle theta. For this system, definitely this mass m will create some initial deflection in a spring K1 and K2. Due to the weight of this mass, the spring K2 will be under pressure and it will be compressed. So definitely we will have some initial reduction in this spring K2, and the spring K1 will be pulled due to this weight, and definitely we will have some initial elongation for this spring K1 because of this mass m. So definitely we will have some initial static deflection, but we will derive the equation of motion using in fact about the equilibrium position after the initial deflection and solve the equation for this system. Okay, here we consider x, which is measured from the equilibrium position. I mean, for example, if this is the equilibrium position, we measure this x from this position, and this is, for example, the positive direction. So in this condition, you can write the potential and kinetic energy. To derive the equation of motion for this system, we can use two different methods. The first option is the Newton's second law, and the second one is using the energy methods. Here I use the energy method. If you wanted to use, for example, Newton's second law, you can easily plot the free body diagram for this system. You know, when this mass m is going down, so the spring K2 will be under pressure. So the reaction of this force will be a upward direction force to mass m, and it's equal to K2 times by x. And also the spring K1 will be pulled, and the reaction of this motion on mass m is again an upward force with amplitude K1 times by x. And now you can write the Newton's second law. We will have the summation of the force in x direction. It must be equal to the mass times by the acceleration, which for this system is x double dot. The summation of the force here is equal to minus K1x and minus K2x, which is equal to mx double dot. So this is the equation of motion using the Newton's second law. As you can see here in the force equation, we neglect the weight. Here, we did not consider the weight in our free body diagram. Here we have one weight. When you plot the free body diagram, you know we have weight mg, and in dynamics, if you wanted to plot the free body diagram, definitely we will have one weight. We will have one normal reaction here. The normal reaction, because it's perpendicular to the direction of motion, it will not appear into the force equation in x direction. But mg, the weight, will have two components, one component in x direction and the other component which is perpendicular to the x direction. But the mg times by sine theta, which is the x component of the weight, in dynamic must be appear in this equation for the force. But here in vibrations, you can see that we ignore this term. What is the reason? Can you tell me why I did not consider the weight in this equation? I explained this in previous sessions. What is the reason? Any idea? No idea? Okay, I explained because in this system, the weight will create some initial deflection. And generally in all of the systems, when we have some initial deflection due to the weights, you can ignore the initial deflection. In the force, for example, here, when you write the force due to the spring K1, I only considered K1 times by X, which X is measured from the equilibrium position. But definitely this spring was under tension, and it has some initial elongation, but we ignored that part in this force term. So we also neglect the weight because we neglect the initial deflection. In previous sessions, I show you for a system with vertical, here in a system with vertical vibration with mass M and a spring K, I explained that if you calculate the equation and extract the equation of motion about the equilibrium position, you don't need to consider the weight and you don't need to consider the initial elongation. If you do not calculate or do not extract the equation of motion about the equilibrium position and consider the weight and also consider the initial deflection, these two terms will cancel out each other. So there is no difference, and we prefer to neglect the weight and initial deflection and directly write this equation of motion without considering the weight. Clear? Is it clear now? Okay. So easily we using the Newton's second law extract the equation of motion. The second method that I used here is the energy method. I use the potential energy here. We have two springs. As I told you, we neglect the weight. So you can see in the potential energy, we neglect the potential gravitational potential energy. I mean, there is no mgh despite this mass m. For example, if we assume this is the datum level during the motion and during the vibration, the level of mass m is changing. But here in potential energy, we neglect this term because due to the previous reason, because if you want to consider the weight in this potential energy, here in the x, in the elongation and reduction of the springs, you should consider the initial deflection as well, which these terms will cancel out the weight during the motion. So easily we neglect these terms to simplify our calculations. We will have only the potential energy into the springs, and we neglect the gravitational potential energy. And easily the potential energy in the spring is equal to half kx squared, which the displacement for both springs are the same. Both of them are parallel. So the deflection for both of them are x. Only the stiffness is different, k1 and k2. And the potential, the kinetic energy, sorry, is equal to the half times by the mass times by the velocity, because here we only have one translational motion. So the kinetic energy is equal to half times by mx dot squared. So easily you can substitute into the term of energy in the equation of energy. We know that T plus U is a constant value because this is a conservative system. So the derivative of a constant value, which T plus U with respect to time must be equal to 0. And we can substitute here for U and T from kinetic energy and potential energy. And you can calculate this derivative. The derivative of this term, half k1 plus k2, is a constant value. X squared is not constant. So the derivative of x squared with respect to time is 2 times by x dot, which 2 will be cancelled out with half. Again, here we have half times by mx dot squared. Half times by m is a constant number. X dot squared, the derivative of x dot squared with respect to time, is 2 times by x dot times by x double dot. Again, 2 will cancel out with half, and we will have mx dot x double dot. X dot can come out from the parentheses, and we will have k1 plus k2x plus mx double dot is equal to 0. As you can see, we extract the same equation of motion here from energy methods and from the Newton's second law that I extract here initially. So the natural frequency is the eigenvalue for this system. I mean, you need to extract or form the characteristic equations for this system. The characteristic equation is m times by alpha squared plus this parenthesis, which is k1 plus k2. It must be equal to 0. This is the characteristic equations. From here, you can extract that alpha 1 and alpha 2 are equal to the square root of this parenthesis, which is k1 plus k2 divided by m plus and minus, and of course we have one I. So this is the natural frequency, which is the eigenvalue for this system. Okay. Also, you can use the Rayleigh's method. I mean, if you want to use the Rayleigh's method to extract the equation of motion, here when you calculate the u and t, you can assume that x is equal to, for example, uppercase x times by sine omega nt or cosine omega nt, and substitute here, and you can easily extract that omega n again is equal to this term. Okay, there is no different. Any question? Is it clear? We obtained the natural frequency for this system. Any questions so far? Okay. What was the difference if we consider x measures from unstretched position of springs? So, for example, assume that before the stretch, the mass m is located here. Yes, and this is the equilibrium position. If you write the equation of motion, as I told you, you should consider the weight in your equations, and only your calculations will be a little more complicated. So by neglecting the weight and calculating the equations and plot the free body diagram about the equilibrium position, in fact, we simplified our equations and we decrease the number of the calculations. Okay, so this is the same point that I mentioned in my explanation in previous slide. Now we want to continue with the free vibration with viscose damping. I mean, we can consider this time a system. As you can see here, we have one spring, one mass. So we had these two components in the previous system, but this time we have one additional component, which is damper. As you can see, if we show the coefficient of a damper by using C, which C is the coefficient of damping, and the force in a damper is equal to C times by the velocity of the damper, which here, when we show the displacement by x, the velocity of the edge of the damper is equal to x dot. So we will have Cx dot if you plot the free body diagram for the mass M and assume that mass M is going down in positive direction of x, we will have one reaction due to the spring, which is K times by x, and we will have one reaction due to the damper, which is C times by x dot. Okay, and Cx dot is the force exerted by the damper on the mass M. And again, I should mention that definitely there are some nonlinear dampers similar to the springs in the real world. But in this course, we only consider the linear dampers because we only want to concentrate on the linear equations of motion and linear systems. So here we assume that the damper is linear. So we can assume that the force exerted by the damper on the mass M is equal to a coefficient times by x dot, which this coefficient is called here C. Now we can extract the equation of motion for this system. Easily you can see this is the equation of motion, mx double dot. This term is added to the equation of motion in the previous section. When we extract the equation of motion for an undamped system, the equation was mx double dot plus kx is equal to 0. But here in a damped system, you can see that we have one additional term, which is Cx dot. Okay, so in the equation of motion, we have one velocity term, and this velocity term will affect on our response, as you will see, and will change the behavior of the system only by adding this C. And sometimes we can control the vibration by using this parameter C. So the characteristic equation, we want to solve this equation. The first step, we need to form the characteristic equation. The characteristic equation is equal to m times by alpha squared plus c alpha plus k is equal to 0. As I told you, the coefficient of x double dot times by alpha squared, the coefficient of x dot times by alpha, and the coefficient of x, which is plus the coefficient of x, and it must be equal to 0. Of course, the equation is homogeneous because there is no external force, as I told you. So here we only deal with one homogeneous equation, and we need only to obtain the homogeneous response or transient response. If you solve this equation using the delta method, you can extract two roots for this equation, for this algebraic equation. We will have two roots using the delta method. You know that alpha 1 and alpha 2, the two roots for these algebraic equations are minus c, which c is the coefficient of alpha, the damping constant, plus minus a square root of delta, which delta is equal to c squared minus 4 times by m times by k, which m is the mass of system, k is the stiffness, and c is the damping coefficient, divided by 2m, which m, as I told you, is the mass. So alpha 1 and alpha 2 can be written in this form: C minus C divided by 2m plus minus square root of C divided by 2m squared minus K divided by m. And we can write the response in this form. As I told you, xt is equal to C1 exponential alpha t plus C2 exponential alpha 2t. As you can see, the solution procedure is similar to the method that I explained in the revision of ODEs and in the previous section. So xt is equal to C1 exponential of the first root times by t plus C2 times by exponential alpha 2, or the second root times by t. But here we will have three different cases based on the value of this term and based on the sign of that phrase below this radical. We can obtain three different cases. The first case is when this term is positive. The second case when this term is equal to 0. And the third one is when this term is negative. When this term is positive, in fact, if you remembered in the revision of ODEs, we had three different cases. The first case was when two roots are distinct and they were real. The second case was when we have two complex conjugate roots, and the third one was when we have one double roots. Here, this term, when this term is equal to 0, this case is a double root. This case is real, two real distinct roots. And when this term is negative, it means that we will have two complex conjugate roots. Now we want to define one parameter, and then we will refer to these three different cases. We define a critical damping constant, or a new parameter. This C stands for critical. It means that this is a critical damping constant, and it's equal to 2 times by m times by omega n, or a square root of k divided by m. And this will obtain when the phrase below the radical in previous slide is equal to 0, as you can see here. We call it critical damping. And when we have a critical damping, we will have a double roots. So by using this critical damping, we define a new parameter, which is called damping ratio. You will see that the most important parameters in a viscous damped system, a single degree of freedom viscous damped system, the most important parameters are this damping ratio and the natural frequency. I mean, when you have these two parameters, you can obtain other behavior and you can obtain other characteristic in your system. So anytime when you want to obtain the behavior of a vibrating system, you need to extract these two important parameters. One is the damping ratio and the other one is the natural frequency. And you will see when you have these two important parameters, you can obtain the response, you can obtain the damp frequency, you can obtain the behavior of the system under different type of loading, and also you can extract the equation of motion easily. So by using this parameter Kasai, which is the damping ratio, you can again rewrite the roots for the characteristic equation. Here you can see the two roots of the characteristic equation can be rewritten in terms of Kasai and omega n. So the eigenvalue for your system can be rearranged as a function of the damping ratio and the natural frequency. This is the damping ratio, and omega n, which is the natural frequency. And you know that natural frequency is equal to a square root of k divided by m, and Kasai, or the damping ratio is C divided by CC, which CC is 2 times by M omega N. So psi is equal to C divided by 2 times by M omega N. So this is the roots, and we can again write xt as a function of psi and omega N. So if you rewrite the xt, the response of the equation of motion, which was mx double dot plus cx dot plus kx is equal to 0, the response can be rewritten as c1 exponential minus psi plus square root of psi squared plus minus 1, which psi is damping ratio times by omega nt. So you can see xt is a function of psi and omega n. The eigenvalues are a function of psi and omega n, and you will see all of the characteristics and even the equation of motion can be extracted as a function of the damping ratio and the natural frequency. Now we will discuss the 3 different cases in previous slides. And here in this slide, we will discuss the 3 different cases. The first case is when psi is less than 1. In this case, that phrase below the radical is negative, and we call it underdamped system. In an underdamped system, the phrase below the radical is negative, and we will have 2 complex conjugate roots. We can write xt in this form because we know this term b below the radical is negative, so we will have one I here, which this I is a complex indicator, and in fact I is the square root of -1. So we can expand this response. We will have c1 times by exponential this term plus c2 times by exponential second roots. We can expand this term. The real part, which is minus psi omega n, can become out from the parentheses, and we will have exponential of real part times by t plus multiplied by c1 exponential of imaginary part, c2 times by exponential imaginary part times by t. Or we can write in cosine and sine form. Again, here you can write the exponential of imaginary part, c3, which of course c3 and c4 are different from c1 and c2. Okay, you can write xt in any of these forms. I mean, you can write in this form, or in cosine and sine, or you can write in only sine form or cosine form. All of them are the same. I mean, in your response, in your equation, if you solve the equation of motion, you can write your response in any of these forms, and all of them are correct, no different, because all of them are equal. You can convert from exponential form into cosine and sine harmonics, or you can convert it into the only sine or only cosine form. So no different. And if you plot the response, you will see an underdamped response in your system that I will show you what is the response for this type of system. And again, these constant coefficients will be obtained from the initial conditions, because these are the constant coefficient in homogeneous solution. And always, to obtain the constant coefficient in homogeneous solution, you need the initial condition or boundary conditions. Also, we define a new parameter, which is called the damped frequency, or frequency of damped vibration, is omega d, and it's equal to a square root of 1 minus psi squared times by omega n. And you can see here the damped frequency is a function again of psi and omega n, or damping ratio and the natural frequency. Again, these 2 important parameters play the main important role in the damped frequency terms. So we can use the initial condition to obtain the constant coefficient in previous slide. And if you use the initial condition x naught and v naught, which x naught is the initial deflection and v naught is the initial velocity, you can easily obtain C3 and C4. If you refer to the previous slide, C3 and C4 are here, the coefficient of sine and cosine. I mean, when x, you can substitute here, t is equal to 0. So we will have the exponential of 0, which is 1, times by C3 times by cosine 0, which is 1, C4 times by sine 0, which is 0. So easily you can obtain that C3 is equal to x naught. And then you can calculate the derivative of this term with respect to time and substitute t is equal to 0 and obtain C4. So you can use this initial condition for C3 and C4, and also you can use the initial condition to obtain x or x naught, uppercase x or uppercase x naught, which they are the amplitude and also the angle phase of your system. But this time, if you want to obtain uppercase x naught and the angle phase, these two parameters, it's not as simple as C3 and C4. You need some more complicated calculations, but you can use these equations to obtain your response. Okay, in the exam, for example, when you have an exam, if the exam was open book, easily you can use these equations and these notes. If it was not open book, and if for example, if it was face to face, I will give you all of these equations, so you don't need to memorize any equations, and I will give you all of the required equations. But you can check and you can search how you can obtain this amplitude and angle phase in this equation, and maybe you can email me your results. Okay, but the second case is when psi is equal to 1. We call it critically damped system. In a critically damped system, the terms below the radical is equal to 0, and the response, which is when we have a double roots, is equal to C1 plus C2 times by t exponential minus omega nt. And finally, the last case, which is called overdamped system, psi is more than 1. So the phrase below the radical is positive, and the response is C1 exponential the first root times by t plus C2 times by exponential second root, or alpha 2 times by t. And you can see both of the roots are functions of omega n and psi. And here you can see this is a equation of motion for the system, and we can write the equation of motion as a function of psi and omega n. You remember that in previous slide, I show you that the equation of motion for a STOF system with damping, with viscous damping, is mx double dot plus cx dot plus kx is equal to 0. You can simplify that equation and you can extract this form of the equation, which in some references, this form is called the standard form of the equation of motion for a damped STOF system. And it's equal to x double dot. You can see the coefficient of acceleration, or x double dot, is 1, and this form is called the standard form of the equation of motion. So here you can see the coefficient of x dot is 2 times by damping ratio times by the natural frequency, and the coefficient of x, which is the natural frequency squared. So if you had the equation of motion in numerical form, and you want to obtain the natural frequency without solving the equation of motion and without solving the algebraic equation of the characteristic, in fact, the characteristic equation, and you don't want to solve these equations, you can easily divide your equation by the coefficient of the acceleration. And then when the coefficient of acceleration, or the coefficient of x double dot, is equal to 1, the coefficient of x is natural frequency squared. I mean, the square root of the coefficient of x is the natural frequency of your system. Okay, and then you can obtain the the damping ratio, the Kasai, by using the coefficient of x dot. So anytime when you have the equation of motion in the exam, especially in the exam when you are in the famine of time, you can use this point easily. You can divide the equation by the coefficient of the acceleration, or x double dot, and convert the equation into the new form. In the new form, when the coefficient of x double dot is 1, the coefficient of x can help you to achieve the natural frequency, and the coefficient of x dot can give you the damping ratio. Finally, this is the general form of the response. If you plot the response for the previous systems, the over-damped system, critically damped, and under-damped system, you can see here, this is the undamped system when Kasai is equal to 0. In previous section, when there is no damping in your system, this is the response. As you can see, that amplitude of the response will be remain constant. This one is overdamped when Kasai is more than 1. You can see this dashed line is for an overdamped system. And the critically damped when Kasai is equal to 1, you can see this is a critically damped, this line. And finally, the under damped system when Kasai is less than 1. And you can see that this dashed line, which by increasing the time, the amplitude of the response is decreasing. Here, based on the value of the Kasai and also the value of the natural frequency, the behavior of these graphs will be changed. And also this initial condition will affect on your response. So sometimes in the exam again, if you had the initial condition, you can use the initial condition and the behavior of your system using the damping ratio and the natural frequency, and you can predict that which graph is for which system or which equation of motion. Okay, any question? If you don't have any question, we can wrap up this session, and after a 10 minutes break, we can start the tutorial session. Any question so far? No questions? Okay, we will have a 10 minutes break and we start the tutorial session after a 10 minutes break. Okay, thank you and see you.